You'll edit it later, right? Okay. So for our first simulation, we have coded only the attractive force interaction between a cluster of particles, with the goal of this converging to a sphere. Now, the initial problem we ran into with this was the fact that when particles got too close to each other, with no collisions coded in, they would accelerate each other off to infinity. And so our solution was, temporarily, to just deactivate forces between particles when they're within a certain radius. And this produced the expected behavior of having the particles clump up into a sphere. For our next interaction, to try to replace the just disabling forces when things are too close, we decided to also add a repulsive force between the particles, but this with a different denominator, an arc to the fourth law instead of an r squared law, so that it would become stronger when the particles became within a certain distance of each other, but not before that point. And this led to an oscillatory behavior in the sphere, which is another, interesting interaction that we're trying to generate. Once again, we have... Wait, what's the difference between this and the last one? Oh, okay. So anyways, I guess, yeah. So this is the same as our last video, but here's where we updated our rendering scheme. So previously, the simplest solution for visualization, since we're not doing the Marching Qubits algorithm implementation until the next week, at first we just rendered it with the cloth being woven through all of the particles in their random initial starting positions. And this just sort of led to a very jumbled mess, which you could still tell the general shape, but it wasn't super useful. And so what we did instead is we graphed each particle as one triangle. To do this, we actually have two dummy particles being set to locations near the original one. And also the other key thing is that they're all facing outwards from the centroid, and this helps to create a a feeling of a surface, which was lacking in the previous version. And then for fun, we decided to see just what these force laws would produce with two clusters of particles at the start, and this shows that, as we expect, the groups overall attract towards each other and then combine into the same sort of bouncy sphere that we've seen in the previous simulations. This works because we are computing the forces between each particle and every other particle as gravity would. The other reason that this looks interesting is because of the normal shading applied to it currently. That's not important, it's fine. And this simulation is our first example of a multi-particle system. And so this one, there are only two, the red and the blue. The red being attracted to themselves and repelled from the blue, and the blue just repelling the red and being repelled by it. And as you can see, the red groups up in the center over time and pushes the blue points out to a cloud, which also contributes to pushing the red points in. Yeah, so starting from our two-particle simulation, you can see here as we add the third particle to the mix. And the behavior this produces is that because overall there's more particles that repel red and attract to themselves in a way, now the blue and green particles group at the center instead of the red. The blue particles, being more strongly attracted to themselves, take the centermost position in the cluster, with the green going around them slightly. One more particle simulation I did to start approaching doing realistic simulations is to do a sort of pseudo proton-electron interaction type force, such that like particles actually repel themselves and are attracted to the opposite, as with charge between protons and electrons, and also that the electrons in this case have a much reduced mass compared to the protons. And as you can see, the effect of this is that the particles form into sort of special structures, because each electron and proton have to find sort of one of the other to pair with in the structure overall, and then as a unit, that's actually like a net neutral unit, and so together then they just sort of vaguely attract to nearby shapes, creating what might be thought of as like very primitive molecular structure. And of course, because of the lack of more complicated interactions, it doesn't form anything really interesting, and just sort of is like one overall grid with these unique internal properties.
You don't say it's uninteresting. It's still pretty cool.
Well, it's just like it could be more realistic. It's not like